Flip a light switch, the lamp turns on, and almost everybody carries the same picture in their head. Electricity leaves the power source, rushes through the copper wire like water in a pipe, and arrives at the bulb to make it glow. That picture is useful for beginners until you take it literally, because if you take it literally, you run into a problem you can't ignore. The electrons in a metal wire don't shoot from the outlet to the bulb at anything like the speed you imagine. In an ordinary circuit, their net drift is slow, sometimes extremely slow. So if the stuff inside the wire isn't racing to the bulb, why does the bulb respond so quickly when you close the switch? That question is where the real physics starts. Now first, we have to clean up the language. People say electricity as if it's one thing. It isn't. You're mixing at least 3 different ideas. Charge is the stuff electrons carry. Current is the flow of charge. Energy is what actually gets delivered to the bulb and turns into light and heat. Current does flow in the wire, no argument. But the energy that powers the bulb, what you actually care about, does not have to be carried inside the copper, the way a truck carries a box down a road. Here's the key idea, and it's the one people resist in a working circuit. The energy transfer is carried primarily by the electromagnetic field in the space around the wires, and the wires mainly serve as guides that shape that field and steer the energy where you want it to go. Let me make that feel less mystical. When you connect a battery to a circuit, charges rearrange themselves along the conductors. That rearrangement sets up an electric field along the circuit. That electric field is what tells charges everywhere in the loop to start drifting. As soon as there is current, that current produces a magnetic field that wraps around the wire. So around a simple wire carrying current, you have 2 things in the surrounding space: an electric field associated with the voltage and charge arrangement, and a magnetic field associated with the current. And when you have both together, physics gives you something powerful, a direction of energy flow through space. There's a formal name for it, the Poynting vector. But you don't need the equation to understand the message. The fields don't just sit there, they carry energy. So what happens when you flip the switch? Important news that the circuit is complete propagates through the circuit as a change in the electromagnetic field. That change moves through space around the conductors at a significant fraction of the speed of light. The electrons don't need to travel from the power station to your bulb. The field sets up, and the energy flow begins. Now think about where the energy actually goes. A bulb, a resistor, a heater coil. These are places where energy is converted into heat and light. In the field picture, energy flows in the space around the wires and then flows into the component from that surrounding field. The component is like a drain in an energy river. Energy flows and gets absorbed where it can be used. At this point, you might ask, if energy is flowing around the wires, why do we even need wires? Great question, because without wires, the field spreads out. It radiates, it gets wasted. Wires shape and confine the fields into a controlled path. They guide the energy from source to load efficiently. They are not just metal pipes, they are part of the structure that controls how energy flows through space. So when someone says electricity doesn't flow through wires, here's the truth: charge flow is in the wire. Energy flow is mostly in the field around the wire. But don't make the next mistake. The wire is not irrelevant. If you break the circuit, the field collapses, and the energy flow stops. So the wire matters because it defines the geometry of the field. Also, real wires have resistance. That means some energy flows into the wire itself and becomes heat. That's why wires get warm at high current. So the accurate picture is this: energy is transported mainly by electromagnetic fields. and delivered into components or resistive materials where it is dissipated. The old picture, electrons as tiny delivery trucks, is misleading. Electrons are more like a cooperative crowd. They shift slightly together. So the field pattern can exist, and the field pattern is what actually moves energy. If you want a final gut check, ask yourself this: what turns on quickly when you flip the switch? Something that requires electrons to travel the whole circuit, or something that requires a field change to propagate? The second one. And that's the key insight. The energy that matters is not trapped inside copper. It exists in the space around it, guided by the wire, delivered by fields. If you remember one sentence, remember this: wires guide charge,